specialization is hydraulics and water resources. Okay, so and basically my research interests are in irrigation engineering and also hydraulics. A little bit of I do a lot of consultancy on bridge hydraulics. So I thought I would share some of my experiences because this course is on, it seems, infrastructure. So infrastructure, whenever we think of infrastructure, we feel that usually the roads,
Sorry,
the building.
sorry,
Yes.
you.
Hello. Yes.
Professor, sorry for interrupting.
Yes. Tell me.
I am Professor M.L. Agarwal. Welcomes
Yes.
you.
Okay. Thank you. Thank you, sir.
Before you start, sir, some formal welcome is there. So I will
Okay.
request our DP.
Okay.
Yes, sir.
Okay. Okay. Please,
Okay.
please.
Okay. Okay, sir. Thank you.
Sorry for the interruption, sir. But
No
we need.
problem. Okay.
Study was a dream, tomorrow is a vision, but a day well lived makes every study a dream of happiness and every tomorrow a vision of hope. Hello, namaste, and thank you for joining us for another session of this 5 days FDP titled Infrastructure Development, sponsored by All India Council for Technical Education and organized by the Department of Civil Engineering, Government Engineering College, Bilaspur. The title for this very first session of the day is Hydraulic Modeling of Large Bridge, presented by Dr. K.S. Hari Prasad, Professor, Department of Civil Engineering, Indian Institute of Technology, Roorkee. He has completed both his Masters and PhD from Indian Institute of Science, Bangalore in the year 1990 and 1996 respectively. Since 1998, he is associated with IIT Roorkee and at present working as professor in the Department of Civil Engineering. He has published around 100 research papers in different prestigious journals and national and international conferences. He has guided more than 70 masters and PhD scholars and also carried out several sponsored and consultancy projects in which a number of projects were in collaboration with different countries like UK, Canada, USA, and more. He received the DAD scholarship under Disaster Mitigation and Prevention Program for tsunami affected country and visiting fellowship of Hong Kong. In the year 2006, he received the Jal Vigyan Puraskar for his research publication. He was awarded with the Best Theoretical Oriented Paper Award for the year 2009 and 2012. Sir, we are deeply thankful to you for joining us for this session, and without more ado, I request you to start the session.
Shall I start?
Yes, sir.
Shall I start? Okay. Thank you.
Yes, sir. Yes, sir.
Okay. So my slides are visible to you. Hello.
Yes, sir. Yes, sir.
Sir, right.
Okay. So actually, the very course name itself is infrastructure development. So whenever we think of infrastructure, we always think of roads, connectivity, then the buildings, and so and when we talk of road network, bridge are part and parcel of any road network. So we have to construct bridges to connect population on either side of a river or a valley or this thing. So bridges are very important as an infra. It is an important component of a infrastructure. So basically, my research or my consultancy is basically whenever you are building a very big bridge, okay, especially on alluvial rivers, okay. So there is a lot of care has to be taken because bridge is a very big because you have to spend a lot of amount of money. So any wrong in the either in the design or in the execution will result in a loss of money. So we have to be very careful before we finalize the bridge alignment, bridge this thing. So in this lecture, So I will be giving a brief introduction of the hydraulic aspects of bridge. Okay, so basically in the bridge construction, whenever you are constructing a very major bridge, so what are the hydraulic aspects which one has to consider, and how do we go about designing the by to for a safe dam design. Okay, taking into consideration the hydraulic aspects. Once the hydraulics is there, then the structures and the geotechnical people, they will be doing the structural components and the design of foundations. But the hydraulic uh, data, hydraulic input is very much necessary for them to safe for their safe design. Okay, so basically a bridge is a structure. Usually we take any bridge which is more than 6 meters, we call it as a bridge, otherwise we just call it as a culvert or something. But usually the bridges are classified as minor bridge and the major bridge. Okay, so the minor bridge is basically if the bridge length is less than 60 meters. Okay, we call it as a minor bridge. Okay, and if it is more than major bridge, it is more than 60 meters, we term it as a major bridge. Okay, but usually even up to 200 meters we still consider as a minor bridge. Okay, but more than 200 meters, so especially when we are designing bridges, while constructing bridges on alluvial rivers. Basically, alluvial rivers have a tendency to shift their course. Okay, so you have to be very careful in fixing the alignment of the bridge. Okay, so basically hydraulics come into picture while during this fixation, and also we know that these alluvial rivers during floods. Okay, so they will be there will be a lot of scour taking place. That means basically the river flow will be eroding, taking away the lot of riverbed material, and so the bridge piers and the abutment should be. So if we want to know what depth the foundation has to go, so that the scouring effect is not affects the safety of the foundations of for the abutment as well as the piers. Okay, so a few definitions are required before we move into the discussion. Okay, so a freeboard. So you hope I all of you are familiar with some hydraulic aspects at BTech level. So I will be if even then I am just giving some definitions. So which will be this thing. A freeboard at any is the difference between the highest flood level. So we should know the what is the highest flood level which would be happening at the bridge side. Okay, so the freeboard is the difference between the highest flood level after allowing for afflux. Afflux means whenever we construct a hydraulic structure as bridge or this thing, there will be an increase in the water levels of the river. So this is what this increase we call it as a flux. And the formation level, so the freeboard is the difference between the highest flood level after allowing for reflux and the formation level of the road embankment on the approaches. That means the bottom of the road embankment, the formation level we call it. So this difference is called the freeboard. So this freeboard is always kept as a safety factor, so that our bridge is always above the high flood level. Okay, highest flood level, or we call it as HFL, is the level of the highest flood ever recorded or the calculated river for the design discharge. Sometimes what happens is, if it is a very major river, so the Central Water Commission and all other agencies, they will be recording the highest flood levels continuously over the and whatever is the highest recorded floods over the past 30-50 years, so that has to be taken into account while fixing the formation level and the other this thing. So this is what we call it as the highest flood level. Okay, and if there are some small rivers, so then they are not monitored that regularly. So then we have to find out how highest flood level can be, we can calculate instead of measuring, because measuring the highest flood levels continuously requires a lot of time and energy. Okay, so they can be calculated with some empirical equations. Okay, so but for major rivers and very important rivers, so usually these highest flood records, highest flood levels are recorded by the central agencies and also state agencies. And the lower water level is the level of the water surface when there is during dry season. Okay, and it is not of that much use as far as the hydraulics of uh, bridges is concerned, but even then we should have an idea of what is the low water level. Okay, then the length of the bridge. The length of the bridge structure is taken as the overall length measured along the center line of the bridge between the inner face of the dirt walls. That means basically the abutments, the two abutments where you have the this thing, and in between you will have piers. Okay, so that length of the bridge is taken as the along the center line of the bridge. Okay, between the inner faces of the dirt walls. Okay, and the linear waterway. The linear waterway of a bridge, basically first we should know, whenever we have to find the length of the bridge, what is the spread of the uh, river, okay, river water surface during the high flood level. Okay, so that is what we call it as the linear waterway. Linear waterway of a bridge is the width of the waterway between the extreme edges of the water surface at the highest. Whenever a very high flood occurs, what is the maximum spread the water surface will attain? That is called the linear waterway. Okay, so there are some empirical formulas. You may be knowing the Lacey's formula finding out the linear waterway, or usually it is also obtained by the measuring. Okay, for very big rivers. Okay, and so this is very important, because this is a very important factor for deciding the length of the span of the bridge. Okay, how much is the length? Because any wrong which calculation wrong in the calculations of this linear waterway will affect the cost of the bridge. Suppose, let us say, if the bridge length is overestimated, so that means it costs an extra money. Okay, so we have to be very judicious while fixing the length of the bridge. Okay, so in that way this linear waterway plays a very important role. And the effective linear waterway is whatever is the waterway, then minus the effective widths of obstructions. That means basically when we construct a bridge, we will be having piers, abutments. So all these, they will have certain thickness. So all these have to be deducted from the overall length of the waterway to get the effective linear waterway. Okay, so if this effective linear waterway should not be too small as compared to the linear waterway. If that is the case, then there will be a choking of the river. That means basically you are constricting your bridge to a very small length, where the water surface elevations upstream of the bridge will be very much affected. So that should be avoided. So that way the effective linear waterway is also an important factor while uh, deciding the length of the bridge. So then the first thing of whenever we design a bridge or is selection of a bridge site. Okay, so the consideration at the time of selection of a particular bridge site includes river training works, uh, and also if there are approach roads. Okay, so then what should we do, whether we have to connect these approach roads, or so what are the factors which will be deciding factors for uh, finding the selection of the suitable bridge site is, uh, if the bridge is up to 60 meters, that means if it is a small bridge. Okay, then the location of the bridge is governed by the approach alignment. That means basically what is the approaches on either side of the river or valley. Okay, you try to connect these approaches instead of going for the best possible these things, because if you the criteria is that the suitable safety or the most suitable site, let us say from the foundation, from the bearing capacity considerations. Okay, if you have to shift it, then you have to shift the approaches also, so that will be very costly. So for small bridges, so the safety considerations, the suitable site, okay, may not be that important, okay, as compared to the approach alignments. That means if I have two roads, okay, on either side of this, try to connect these two approach roads with a bridge instead, even if the soil there, it may not be of that uh, strong or something. Okay, so we have to, so basically there the alignment overrides the suitable these things. And bridges having toll lengths between 60, and basically these are minor bridges because they do not cost much. So even if you take the foundations quite low, so the cost may not increase that much. Okay, so that then you have minor bridges, so it is 60 meters to 300 meters. Here also requirement of a suitable bridge site and proper alignment of approach is considered together. Here both them. So which is so there will be an economic analysis. Okay, what is the suitable site and what happens if I connect the approach roads. Okay, so whichever is the minimum, so we will go for that. Okay, and bridges having total lengths more than 300 meters, then you have to be very careful, and you have to select a site which will be that will be the overriding consideration as compared to the approach alignments. That means approach alignments are given not that importance as compared to the suitability of the site. Okay, so am I audible? Hello.
Yes, sir.
Yes, sir.
Okay, so if you have any questions, please you can rise. Okay,
Sure,
otherwise
sir.
it becomes a little monotonous. Okay,
Yes,
so
sir. Yes, sir.
because we are not on the because I am not seeing anybody, so it becomes monotonous. Okay, there should be some interaction.
Yes,
Okay.
sir. Yes, sir. Yes, sir.
Okay.
Sir, excuse me, sir.
Yes.
Sir, excuse me, sir.
Yes. Tell me.
Very humble feedback, sir. Some of us are from different background, not from civil engineering. So
Okay.
I hope you will be taking care of us also, sir.
This is what I am giving very general. No, I am not going
Yes, sir.
anything.
Yes, sir.
There is,
So far it is very general, sir. Yes.
no, it will. This is what Professor Agarwal also told me, because
Okay.
so you have to take into account the consideration the people who are. But I will be giving only general. Okay.
Yes. Yes, sir.
Only
Thank you.
what are the hydraulic aspects that is required. Okay, for while constructing a major bridge. Okay, and
Yes.
I will also give some experience of what we have done. Okay, so that you will also. Okay.
Okay, sir.
So basically, what I am trying to tell here is that if the bridge site, if it is a small bridge, then you don't give much importance to the what is the site condition. Only if there are two approach roads, because approach roads are already built. So just you try to connect it over a bridge. Okay, so that will save a lot of money. Okay. Suppose if I shift this to a other place, then I have to take these approach roads also, no? Okay, so that's why the alignment is given importance for small bridges, whereas for a very big bridge, a major bridge, because it's a very major structure, so we have to be careful. So there, the site conditions override the alignment conditions. Okay. Hello.
Yes. Yes.
Okay.
Yes.
So
Yes.
then Yeah, so there are two aspects, hydraulic aspects, which we have to consider while hydraulic aspects while designing a very major bridge. One is that what should be the cover which will be taking place. How many of the people know the cover? Cover. Hello.
Yes, sir.
50% maybe. Some
The
50%
cover
maybe.
cover is basically when see when the riverbed material, okay, during high floods, okay, the velocities will be very high in the river, isn't it?
Yes, sir.
So it takes away the bed material along with the flow. Okay. So
Yes,
this
sir.
phenomena of taking away of the bed material from the by the flowing water during high floods is called the cover. Okay. And during low flows they get deposited. Okay. So from the foundation point of view, we should know what is the maximum cover that will be happening in the river, so that we take our foundation levels much below this cover levels, okay, so that the foundations will be safe. This is one aspect. Okay, so that we will come from the hydraulics. We should know the river hydraulics. And the second one is, we know that when we construct a bridge, okay, after, so there will be approach roads. Approach roads are basically the on the either side of the bridge. Okay, so you may be constructing the bridge very well, but if you don't protect these approach roads, okay, so then they are prone to damage during high floods. Okay, so
Like one happened in Bihar.
yes,
This rainy season,
uh,
very newly constructed bridge that collapsed at the approach road.
that collapsed. Okay, so that may
Yeah.
be not that may not be actually I do not know what is the reason, maybe, but the thing is, because the new bridge when it gets constructed, then there must be something wrong with the either the during construction or what all taken, but a very well constructed bridge, very well designed and constructed bridge should should be should be safe in two aspects. One is that the foundations of the bridge should go, the level should be well below the cover levels, okay, and proper river training works should be given to protect the approach roads. Okay, that's what that we do it by providing a guide buns. Basically the guide buns are just next to the bridge, which we will be taking on the upstream of the bridge, okay, to protect the approach roads. Okay, so that we will come into we will this we will I will be discussing in another few slides. Okay, the size, shape, and so the hydraulic what are the data which is required for the bridge site hydraulic data while designing a bridge is the size, shape, and surface characteristics of the catchment, so including percolation and interception. So basically we should know what is the type of catchment. That means catchment you must be knowing. Okay, so catchment is whatever rainfall falls in that catchment that will be contributing to the flow of the river over which this bridge is being constructed. Okay, and the second is the slope of the catchment. What is the slope? Okay, the possibility of subsequent changes in the catchment like afforestation, deforestation, urban development. Okay, so this is also required. Okay. Yeah. The intensity, frequency, duration, and distribution of rainfall. So how rainfall is occurring in the catchment, okay, and How many of you know hydrographs? Hello?
Sir, hydrograph is a study of the previous year rains.
No, hydrograph is basically a relationship between the time and the discharge at the outlet of the like river. Okay, so we will be getting the discharge. We will be measuring the discharge over time. This will give you what is the highest discharge which will be happening. Okay, over the year. Usually for major bridges, the Central Water Commission, you might have heard Central Water Commission, those people have what we call it as gauging sites. Okay, so they will be measuring the they will be plotting the hydrographs and also the highest flood levels. Okay, for major rivers like Yamuna, Ganga, okay, all those things. But small rivers, the state government agencies they do it, but for other things we have no other way, but we have to compute the flood levels and the discharge, the maximum discharge by some empirical relationships.
Sir,
okay?
Excuse me, sir. Excuse me, sir. Sir, when you say level, what is the reference point, sir?
The reference point for this highest flood levels is the mean sea level.
Mean sea level, yes.
Mean sea level. Okay.
Because river bed will be changing always.
River will, you are exactly same. So whatever HFLs they give, okay, all the central water commissions and whatever with this thing, that is taken as mean sea level as the base, okay.
Yes.
As the datum, okay. See, the discharge, the maximum discharge which we can get. Suppose if it is a major river, I told you that central government agencies will be doing. But if we do not have that data, okay, then we can compute the design discharge using a rational formula where CIA, where A is the catchment area, I is the rainfall intensity, and for a given time of concentration, and C is a coefficient which takes we call it as a surface runoff coefficient. C is so which is less than 1. So this rainfall intensity, okay, is for a duration which is we call it as the 1 minute. Is the time of concentration. How many of you know time of concentration? Hello?
Time to reach to the furthest point.
The time, actually, let us say I have a catchment of, let us say, 10 square kilometers. Okay? And all whatever rainfall which is occurring on this 10 square kilometers will be reaching the outlet. Okay? So when the rain occurs, the water which is falling very near to this outlet will be reaching the outlet first as compared to the rain which is falling at the farthest point, isn't it? Hello?
Yeah.
So the time of concentration is the time for the rainfall which is falling at the farthest point in the catchment to reach the outlet or the bridge site, wherever it is. Okay, so this is called time of concentration. Okay, so this time of concentration, let us say it comes as 1 hour. That means time of concentration, if I say 1 hour, okay, it means that it will take 1 hour for the rainfall which has occurred at the farthest from the outlet to reach the outlet. So that means that 1 hour. So that means after 1 hour, if the rainfall is continuing, that means the entire catchment will be contributing. Less than 1 hour, only a part of the catchment will be contributing to the flow at the outlet. Okay, once we know this time of concentration, we can compute the Q. And how many of you know return period? Here in this capital T is there.
Yeah, yeah.
This is called the return period. How many of you know the return period? Let us say if I say let us say 50-year return period flood, what does it mean?
Means same type of rains will prevail there. Pattern of the rain will be same.
No, 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 no.
Hello, sir.
Yes.
It is the time interval during which a given storm is likely to be equaled or exceed.
Yeah, this is what I can say, that return period is that period at which it is expected that a magnitude of that flood will occur once in that. Let us say if I have a 50-year flood, that means such type of flood is likely to occur once in 50 years.
Likely to be equaled or exceed.
Likely to be occurred or exceeded. Okay, whatever will be.
Yes.
Okay, but is 50. So for major bridges, because we are putting a lot of this, usually the time return period is taken as 50 years. If it is a small bridge, so we may go for 25. So what happens to the flood magnitude with the return period? Increases or decreases? Let us say I have a 20-year flood and 50-year flood. Which one will be more?
50-year flood.
50-year flood. That means such a flood, 50-year flood, isn't it? So the greater the return period, higher will be the magnitude. Obviously, isn't it? Hello?
Yeah,
Yes,
it's all right.
Yeah.
it's a very
So basically that is also important while constructing, while computing the discharge. Okay, Q. Okay, so but usually for major bridges, this Q is got by measuring by the central agencies. Okay, so we have to resort to those because they are much more reliable than computing using this empirical formula. If there is no other data is available, then we have to go. So basically the time of concentration depends upon the slope of this thing. If it is a steep slope, the time of concentration will be less. If it is a lesser slope, it will be more. And this C is the coefficient of runoff. Okay, so this will be for urban areas, which will be very high because there will not be any infiltration into the soil. So a lot of water will be flowing on the uh, uh, surface itself, because you have a lot of impermeable surfaces like roads, okay, buildings and all. So that's why, so it will be very high. But if it is a forested or vegetated area, the coefficient will be much less, maybe 0.3, 0.2, depending upon the type of vegetation. Okay, so the maximum depth, then this is how. So once we get the maximum discharge for which the bridge has to be designed, and the maximum high flood level, although then we have to compute the scour. As I told you in the beginning, what is the scour? Scour is the maximum, the scour, which will be a phenomena which the flowing water will be taking away the riverbed material along with it during high floods. Okay, so this phenomena is called the scour. There are two types of scours. One is the clear water scour and general scour, and other one is the local scour. Okay, so the general scour is one. Let us say if I do not have any bridge, whatever is the scour which takes place during the high floods is called the general scour. Okay, suppose now if I construct a bridge, what will happen to the riverbed material very near to the piers? Hello? Hello?
Yes, sir. Yes, sir.
Yes.
So let us say if there is no bridge, even then the cover will be taking place because of high floods there will be a taking away of, this is what we call as the general cover. Okay, what is the average cover depth which will be happening when there is, suppose now I construct a hydraulic structure such as bridge. So whenever we construct a bridge, that means it will have piers and the abutments. Okay, so what
Yes.
will happen to the cover very in the vicinity of this pier? Will it be more or will it be less as compared to general cover?
That will be more, sir.
That will be more because the velocities there will be very high because you are constricting the width, isn't it? Okay, so this is called, hello, there is, this is called the locals cover. Okay, so obviously the locals cover will be more than the generals cover. So we should know what is the generals cover, how much will be happening, and also what will be the locals cover which will be occurring at the bridge piers and the abutments, so that we can compute. Okay, so usually these covers are the cover depths are governed by the soundings. Okay, for the taken. Otherwise, we also have some formulas. Okay, so all these formulas are empirical in nature. So on what factors this cover depends? Can you can you
Discharge of the river, sir. The
yes,
discharge of
yes,
the river
yes.
and the silt grade or silt charge.
Exactly. So the flow characteristics is the how much is the discharge. Higher the discharge, higher will be the cover because the velocities will be high. And the second thing is what type of bed material it is. If it is very small bed material is very what type of so we should know the grain size distribution or the silt factor we call it as. Okay, so these two factors govern the cover. Okay, so usually it is obtained either by soundings or by empirical equations. Okay, allowance is made in the observed depth for increased cover. So usually if I know the uh, design discharge, I will be computing this cover maybe 25% more of this discharge so that we should be safe. Okay, the increase in velocity due to obstruction in flow caused by the construction of the bridge, the increase in covered in the proximity of the piers and guide buns. This is what we call it as the locals cover. Okay, so there is a formula. Okay, so this is a very what we can say, it's a very well known and a very well a tested formula, I can say. Okay, even though it is developed quite long time back, but it has been found to be very useful. Okay, from so this means cover depth is given by 1.34 times q square by ksf whole to the power of 1 by 3, where q is the discharge intensity per unit width. Okay, and if you see here, I am measuring the maximum, this is the means cover depth, dsm is given by, so we are measuring this means cover depth from the full supply level or the HFL, high flood level. Why? We know that the cover is occurring from the bed, but why are we taking the datum as the full supply level for maximum cover depth? Any idea? Hello, are you able to see this figure?
Yes, sir.
See, I am measuring the maximum cover depth. This is not. I have written FSL. Actually, that is not FSL. You should take it as HFL. There is some mistake. Okay, it should be HFL, high flood level. I am measuring the maximum cover depth from the HFL, not from the bed. Why are we measuring like this?
Sir, because this equation is based on the discharge. So discharge is involved. So when we take the discharge, maximum discharge, then the level is at high flood level. So it should be measured from the high flood level.
No, not discharge. See, basically, here this, if I take this bed, river bed as the datum, this will be changing with time, isn't it? Sometimes it will be there, it may be there. So there is no hard, but FSL remains same for a given discharge Q. That's why we take this, the cover depth we measure from the high flood level. Okay?
So,
Okay, sir.
here why don't we go in for mean sea level, sir?
No. See this HFL will be, let us say, 132.5 above mean mean sea level, let us say. Okay?
Yes.
So then I compute this means cover depth DSM using this formula. Okay? 1.34 into Q square by KSF whole power 3. So let us say it has come from, let us say 15 meters. Okay?
Yes.
So then what will be the level of the means the cover level with respect to mean sea level? 135 minus 15.
Yes.
That will be how much? 120. 120. So when you design your foundation, okay, you should take out your foundation level much below 120.
Yes.
Okay, is this clear?
Yes, sir. Yes.
So this HFL is given above mean sea level. Then I compute the means cover depth using this formula. So if you see in this formula, you have the discharge Q, it is coming into picture, and also the silt factor. Basically, this silt factor KSF, it depends upon the type of material. So we do particle side distribute. That what we do is we take the samples from the river bed samples. Okay, we do the particle size analysis. Soil mechanics, particle size distribution analysis, sieve
Yes,
analysis.
sir.
So
Yes,
we
sir.
plot. So we plot that. From that we will be getting this KSF. Okay. So once we get this means cover, so then I will be knowing what is the covered bed level with respect to mean sea level. Okay. So basically I am deducting whatever HF this mean DSM from the HFL level. So then my foundation should go much below this so that my foundation will be safe. Okay. So this is the I have given a small what is that a table. What is the value of silt factor KSF for different? It is fine silt, it is 0.5. So and for heavy sand, it goes up to 2. Okay, so it ranges from 0.5 to 2. Okay, so depending upon the type of material, so we will be doing the sieve analysis. From that, we will be getting what is the type of soil it is, okay, bed material it is. So from that, from this table we can take out the silt factor and compute the means cover level. Okay, so this is what, so this is the first and for safe design, okay, the minimum foundation depth from circumference should be 1.25 times ds. Okay, so what does it mean? Let us say in the previous example, so my, let us say HFL is 135. Okay, and my DSM is 15. So I have my cover level up to 120. So what is the depth of foundation level I should keep? Hello. This is 1.25 ds. So ds is 15 meters. This is 1.25 ds. How much? 15. 150.
18.75.
18.75. So what will be my foundation level now? With respect to mean sea level, 135 minus 18.5.
75.
That will be 116.25.
116.25.
160. That means basically you are going around 4 meters well below the maximum cover depth which would occur. Okay.
Yeah.
That much safety you are giving it to the foundation. Okay. But if it is a major bridge, sometimes you may go up to 1.5 times. Okay. So but this is what the IS code says. Okay. So another aspect. So this aspect. This is one aspect where we have to find the for fixing the foundation of the foundation levels of the bridge
So,
piers.
sir,
And
sorry
yes.
to interrupt you. If suppose we get that some hard rock is there
Okay.
in the vicinity of the scouring depth
Okay.
at a particular location, then we'll go up to hard rock or we'll explore even the hard rock or
No,
reaching to the foundation.
No, if it is a hard rock, we will go up to only hard rock.
Okay. Okay.
Okay. See, this
Okay.
is one aspect. Sometimes what happens is actually the foundation level is also governed by the strength of the material. That means from the geotechnical point of view.
Yeah.
So if that requires that you should go still below, then you have to go.
Yeah.
So there are two aspects. One is from the cover considerations, and another is from the bearing capacity considerations. Okay.
Okay.
You have to compute both of them, and whichever is the minimum, you have to go. Whichever is that means the foundation level, whatever you fix it, should be safe from the cover consideration, and also it should be safe from the bearing capacity considerations. Okay. Then the second aspect is river training. That means, okay, once we have taken the proper care of while designing the bridge structures, like what should be the foundation level, and once we know this, then the geotechnical engineers and structural engineers will be designing, okay, all these things. But now so this will be the part, but the approach roads, okay, if I don't properly guide water, the river, to go below the bridge, okay, it will be affecting the approach roads. So we have to protect the approach roads from the during high floods. Okay, so that is taken care by providing guide bunds. Okay, so this is what we call it as the river training works, which are a part and parcel of a bridge design. Okay, waterway, and I will now skip to this is what. So usually the guide bunds are uh, designed using IRC 89 1997. Of course, there is one more revision has come. Okay, so basically alignment of approach embankment, pattern of flow remains uniform through all the spans of the bridge. Basically, the main objective of providing guide bunds is to see that the river doesn't change its course. Let us say I build a bridge today, and if I don't properly train my river, it may shift to the other place. Let us say let us say it shifts to the right. Then the base on the left, or whichever we have constructed, they may become waste. isn't it? Because the water will not be flowing there. But whereas on the right side you have a problem, because there will be a lot of concentration of water on the right side. So basically that means if I don't guide my river to flow well below the bridge sector, there is a possibility of river shifting. Okay, so to avoid this, we construct guide bunds, and also these guide bunds, okay, will protect the approach roads. Okay, so there are different types of guide bunds. Okay, one is according to their form in plan. One is divergent guide bunds, convergent guide bunds, and parallel guide bunds. So this is, are you able to see these figures? Hello?
Yes, sir.
Yes, sir, we are able.
So this is divergent upstream. So basically this is my bridge axis. Okay. So it is basically I am guiding my water from this thing, and it is approaching the bridge in a constriction. So this is the convergent upstream. That means basically it is widening at the bridge axis, but whereas it is and this is parallel. Usually most of the times we go for parallel. Okay, because we want to see that the water moves means uniformly over all the spans. So basically this is what we here you can see the stride. So whatever whenever you see, basically there are uh, to a certain length of the upstream of the bridge, it will be straight. Afterwards you give a curvature. Okay, so this curvature is given to see that the water flows, the streamlines are formed nicely, gradually. Okay, we don't give like this, like abrupt, like this, because there will be concentration, so there will be a smooth transition is taken place. So basically we have a straight portion followed by a circular, this is what we call it as the nose, okay, of the guide bun. Okay, and there is also one more thing, is we call it as the elliptical guide buns, where from the axis itself we give an elliptical shape. Okay, so elliptical shape starting this like this. So basically this is the major axis, and this is the major axis, and this is the minor axis. Okay, so knowing these two we can get this. Okay, these are called elliptical. So these are these elliptical guide buns are used when the river is erratic in nature. That means sometimes it goes on the right side, sometimes it attacks the bridge on the right side. So if it is erratic, so for a smooth flow, okay, we use this. So once we construct this, we know that this is the bridge, okay, and this is the approach. Okay, so these approach alignments are also protected. Okay, so otherwise if I don't have this, so there is always a possibility that this, even though your bridge is safe, the alignment, the approach roads may not be safe. Okay, in case of acute curved channels, okay, so we go for uh, the flow of after striking the mole head does not follow the profile of parallel guide buns with circular heads, but separates from the boundary as illustrated. Sometimes if the nature of the river is like this, the flow is like this, there is a acute curves. Okay, so then it is, so some portion of the bridge here, they may not, it may not be getting water. Okay, so all these bays may not be that good, but we have no other go but to do that. Okay, length of guide buns. So what is the length we should uh, provide? The length of the guide bun is usually 1 to 1.5 lengths the length of the bridge. That means if my bridge length is 800 meters, So I should provide on the upstream of the upstream of the bridge. If you see here, see the guidelines are given both on the upstream as well as on the downstream. Okay, so this is the upstream. Usually the upstream guidelines will be of a very high length as compared to the downstream guidelines. Usually for upstream, the length of the upstream guidelines will be 1 to 1.5 the length of the bridge. Okay, length of the bridge itself, let us say if it is 800 meters, this will be 1200 meters. Up to that you have to give the guidelines. Okay, then you have a circular mole. Okay, so but whereas in this downstream, okay, it is not that much, it is only 0.2 to point. Why is this? Why we have to give more on the upstream? Why we have to give less on the downstream? Any idea? Why the guideline?
Sir, discharge is already aligned, sir.
Where? Where? Discharge, you are correct. Say upstream of the bridge, you have already aligned, okay, by constructing a this, okay. So that when it meets the natural channel downstream of the bridge, there will not be much problem, isn't it? Whereas on the upstream, you have to guide it, okay. You have to guide so that it comes well below the bridge, okay. So that's why you need a higher length to train the name itself, it tells that river training works. You are training the river so that it comes well below the bridge. So for that, on the upstream you need a very high length, very greater length. This is usually 1 to 1.5 length when there is no model studies are there. This is the IS code says, okay. But if it is a major bridge and if the costs are going very high, so then we have to go for model studies, and model studies will be will tell what is exactly how much is required, okay. So they will be doing some trial. So I will be talking about these model studies in also covering, okay. So on the downstream side, it will be 0.2 times L is generally found to be adequate, okay. Is the downstream guideline is to ensure that the river does not attack approach embankments. This is the only way, okay, because it tries to regain its natural width after a certain distance, okay. Curved head and tile for stride guidelines. These are all the some design considerations which you will be getting in that what is that, I have given you this IS code. It is already available, you can download that. IRC 89, Indian Road Congress 89 1997, okay. So it has given all the details, so you can go through this. And this is a very simple one, I am not going to. And also a slope protection. So once we get, basically these guidelines are earthen embankments, they are not made of concrete, okay. So because this, so you have a side slope on the river side of the earthen slope of guidelines are protects against river action by covering them with stones and concrete. So basically we will be giving the pitching, okay, on the river side, whereas on the other side we may not be giving the pitching, but we will be just growing grass or some vegetation so that the slope is stable, okay. Real slope be protected against ordinary waves splashing by 0.3 to 0.6 clay or silty earth and turf, okay. Pitching on the river side slope. So you have some design calculations. P is the thickness of pitching is given by 0.06 Q 1 by 3, where the Q is the design discharge. Upper limit is 1 meter and lower limit is 0.3. So that means you have to give a minimum of 0.3 meters then pitching thickness pitching. The maximum is around 1 meter. Okay. And another one aspect is that, so this is, let us say this is my guide bund. Okay. So once this is the guide bund, so this will be my river. Okay. If I don't protect, protect this portion, okay, so the scouring will take place here, isn't it? Hello?
Yes, sir. Yes, sir.
Yes,
So
sir.
the once this cover takes place, so this embankment, this slope will become prone to damage because of this covering factor. So to protect this slope, we have to give what we call it as the launching apron. Okay, on the river bed, this will be on the river bed. We will be putting, okay, so that when this cover takes place, this launching apron will come down and it will stabilize this thing. So this is what we call it as the launching apron. This is the toe. So basically for toe protection we need the launching apron. So the launching apron shall be for the protection of toe. The size and shape of apron depends upon the size of stone, thickness of launched apron, uh, and also we put a one toe wall here. Okay, a toe wall which will be protecting this against cover. Okay, so a width of launching apron will be equal to 1.5 times D max, where D max is the cover depth, is found generally satisfactory. That means basically on the river bed, you will be putting a stone pitching of or a launching apron of 1.5 times D max. Okay. The thickness and others are given in this, so I am not going into details. So now do you understand what is the objective of these guide buns and why do we need launching aprons? Hello? Hello? Hello?
Yes, sir.
Yeah, basically launching apron is required to protect the toe so that when the covering takes place, this launching apron will go down and protect the guide bun slope. Okay, if you don't give it, okay, so you will have a problem. Okay. So now model studies. This is where actually I have done some, I do a lot of consultancy on these model studies. Whenever there is a major bridge, especially if the bridge size is more than 800 meters, okay, so the IS code and the IRC suggest that to fix the guide band length and fix the axis of the this thing and know the cover depth, so one has to go for model studies. Okay, that means basically you prepare a model of the bridge and the river, okay, and do the analysis, find the cover pattern and what should be the length of the guide buns for safe design. Okay, so the scope and objective of model studies are the finalization of bridge siting and its waterway causing uniformity in flow distribution, information on estimated and observed maximum depth of cover, design of river training works. These are all given in IS code, but the thing is, for major bridges, the IS code and the IRC suggest that get the model study. From the model study, whatever is got, that is more effective than the design which you use using IRC codes. Okay, and so that's why the model studies are done for major bridges. Okay, before they are constructed. Quantification of general direction of river course through the bridge. What is the flux? What is the effect of backwater? And also one more thing is that effect of presence of flood control and irrigation structures, if any, in the vicinity of the bridge. let us say all these IRC codes which they have given, they have considered that there is no other hydraulic structures in the vicinity of the bridge which is being constructed. But there are already some structures are there. Then what will be their effect? That can be only we can find out by doing model studies. Okay, so in that way there is no other go but we have to go for model studies. Okay, how do we do the model studies? What are the data requirements? The data requirements is that river plan should be there, 3 times the bridge span upstream of the bridge and 2 times the bridge span downstream of the bridge. So we should have a river plan and the river cross sections at 250-meter intervals for each for the entire reach, and what are the maximum recorded peak discharges and maximum flood levels. Okay, and what are the sediment properties such as particle distribution and all those things. Okay, so we have done such a lot of model studies in our lab. Okay, for major bridges. Okay, in Uttar Pradesh, basically Uttar Pradesh and Delhi area, we have done a lot of very around 7-8 model studies. One such model study is on River Ganga, where you must be knowing this Lucknow Agra Expressway, UP. Okay, so it was constructed during Akhilesh Yadav's regime around 6-7 years back. Okay, so there were two major bridges which had to be constructed on this highway. One is on river Yamuna at Firozabad, and one at on river Ganga at Kanaus. Okay, so we have done both the model studies, but here I am presenting the model studies of on river Ganga at Kanaus. Okay, so this is the plan of the river stretch at the bridge site. Okay, which is given. Okay, uh, from the client, and this is usually they will also give us the general alignment drawing of the bridge. Okay, this is the GAD. Okay, so how many number of piers and what is the shape of the piers. Okay, and what is the bridge span length. Okay, this HFL and formation level, all this data they have given us. Okay, apart from the available water level data, the water levels at other usually they get only they give the water level data at high flood level. So, but we can always get it for different discharges using Manning's equation. So, how many of you know Manning's equation? Hello.
Sir.
All civil engineers
All
and
civil
mechanical
engineers.
people.
Okay.
All
Okay.
civil engineers know, sir.
So, okay, so basically Q is equals to A by N R power 2 by 3 S power half. So we construct the for different levels, we construct the what it will be the area. So once that we know the water surface, the using Manning's equation, because this N also we can get from knowing the riverbed material, we can get the Manning's N using Strickler's formula. From that we can compute this. Okay, so the model, so usually all the model studies are done by the Froude number similarity. Okay, so basically the main driving force in open channels or the rivers is the gravity. Okay, so gravitational forces dominate over the other forces. So for dynamic similarity, okay, we use Froude number as the basis for similarity between the model and the uh, prototype or the prototype. So what it means is that the Froude number in the prototype should be equal to the Froude number in the model. How do we compute Froude number? Any idea? Hello? there is a little mathematics here. I do not know, many of you may not be remembering, or especially if you are not from hydraulics.
Sir, basically, sir, it is a ratio of inertia force to the gravity force.
Exactly. It is the ratio of inertial forces to the gravitational forces, and it is given by V is equal V by root Zy. Okay, where V is the velocity, okay, and Y is the depth of flow. Okay, for a wide reverse, actually V by root Zd, where D is the hydraulic depth. For wide reverse, it becomes the uh, depth of flow. So V is equals to root Zy. Okay, so this Froude number similarity, what it says that whatever is the Froude number at the field, at the real real structure where you are constructing, okay, V by root G should be equal to the Froude number in your model. Okay, so that means VR is the velocity scale. Okay, so that means you have to choose your length scale and this thing such that the Froude number both in the model as well as in the prototype are same. Okay, so that is what I have written here. VR by square root of GR LR is equals to 1, where VR is the velocity scale and GR is the acceleration, so that becomes 1, and LR is this. Okay, so basically from Froude's similarity, for the discharge ratio you will get as Q prototype is equals to Q model into LH into LV. Okay, where QM is the model discharge, LH is the what is the length ratio between the model and the prototype in horizontal direction, and LV is the what is the length ratio between the model and the prototype in vertical direction. See here, if you see here, I have given different scales both in the vertical direction and the horizontal direction. Why is it given like that? Any idea?
Because the dimension of river or width of river is much more in comparison to depth of flow. That is exact distortion in scale is there.
Exactly. See, because if I give the same scales both in the horizontal and vertical direction, let us say I am taking I'm constructing a bridge of, let us say, 1 kilometer. Okay, so I have to now represent my river around 4 kilometers upstream of the bridge and 3 kilometers downstream of the bridge. So how much total? It will be 7 kilometers. Okay, and the width is around 1 kilometer is the bridge width, so maybe I have to go a little this way, around 1.5 kilometers. Okay, so my if I take the same scale, and the depths of flow, maybe maximum you will be having 20 meters depth of flow. Okay, even during high floods, let us say it is 15 to 20 meters. If I take the same scale for both horizontal and vertical direction, so the flow depths will become very small. Let us say 7 kilometers. If I take a scale of 1 in 100, okay, so how much will be the length in the horizontal direction? Around 7 meters. And what will be in the vertical direction? 15 meters by 1 in 100. You will be getting very small depths, around 1 around 3 mm, 4 mm. So which it is not possible to really, in that surface tension effects will be very high. Okay, so we have to go for distorted scales. That means the vertical scale will be, let us say here I have given for this Ganga bridge, I have given the horizontal scale is 250. Okay, whereas the vertical scale is 50. Are you able to see LV and LH? Hello?
Yes,
Hello?
sir.
So there
Yes,
is
sir.
a distortion in scale. This distortion in scale is necessary to see that we get enough depth in the model. Okay, otherwise it is very difficult to you won't get meaningful results. Okay, so the discharge scales the geometrically has the following advantages. Okay, this has been found by research also. Due to increase in water slope, it provides sufficient reactive force for bed movement. It also provides sufficient water depth and hence easier to measure. It increases the Reynolds numbers, which results in decrease in surface resistance. That means basically the surface tension forces are become negligible. Otherwise, when the flow depths increase. Okay, if it is small, then you have to take surface tension out. Then there will be a lot of problems with the scaling. Okay. So then we will decide depending upon what is the discharge which we have. Okay. So this is what I am giving some photos of the model study which we did for this. So this is the model which we have. This is under preparation. Okay. See what we did is we have made, so the bridge may be somewhere here. So in the vicinities of the bridge, we have made the bed mobile. Okay, and far away from this we made it rigid because it was becoming very difficult for us to make the entire thing as a mobile bed. Okay, so because we were interested in the cover pattern very near to the bridge. Okay, so this is so we have made around 1 kilometer upstream, up to 1 kilometer upstream of the bridge, and around 0.5 kilometers downstream of the bridge we made the bed mobile, and beyond this we have made it rigid. Okay, so this is the bridge. Okay, and you can see. Okay, so we are measuring the velocities here. Okay, at a different base. So these are the piers. Okay, and this is the abutments. Okay, so this is without any guide buns we are running. Okay, so this is the, and we are measuring the velocities. Okay, so then the water levels. Okay, and the sponsors, they came to see the model. Okay, see here actually this photo is not that good. Okay, because we had also had guide buns here. Okay, somehow I'm not able to show it in a proper way. Okay, so this is the, this is after the scouring has taken place. So how the river bed looks like. Okay, once we stop this. Okay, so this is what we have done, and we have given the recommendations what should be the scour depth and all those things. Okay, so this is what we keep doing. We do a lot of consultancy on such. Now we are doing for a major bridge on we have also done for on river Yamuna near Nizamuddin. We have this, what is that, Delhi Meerut expressway. There were two bridges were coming, which already now they have constructed it. For that also we have done. Okay, so these are all the things which we have done. I think now I have covered. Hope this the model roughness. How do we decide the model roughness? That is also on Froude number similarity. Okay, so this if you want I can share this material with Professor Agarwal. Okay, this PPT I will send him. So if somebody is interested, they can have a look about it. Okay, so I think these are
Okay,
all
sir.
more mathematical. So I want to skip it. Okay. So, okay, thank you. Any questions, please? Professor Agarwal.
Thank you so much, sir.
Okay.
If someone wants to ask something from sir, is there someone who wants to ask anything?
Sir, during the construction of model, there are various deformation, or we can say distortion. like geometrical, material, scale distortion, and also property of hydraulic distortion is also there. So
Okay.
how it is incorporated in prediction the results?
See, the thing is, see, when we are doing the mobile bed here, okay.
Yes, sir.
So
So
in the
many
mobile bed,
distortions are
so
there. Yes, sir.
so the grain size, the soil particle size in the model will not be equal to the same as the what is that in the prototype,
Yes, sir.
isn't it?
Yes,
So
sir.
that also what type of what should be the grain size, that also we can find out by using this fractal shear stress theory. Okay.
Yes,
If
sir.
you see that in my presentation, okay, last three slides I have just went through because it was more mathematical. Okay, so the
Yes, sir.
tractive shear stress theory you can use to get the what should be the bed material. Okay, I will show you the equation. See here, the shear stress tau star, okay, what should be the sediment size in the using a modified form of Shields curve by Rangaraju provides the relation between the non-dimensional critical reactive shear stress tau c dash and the non-dimensional parameter R1. From this we can get the what should be the sediment size in the model.
Okay, sir. Sir, there is
Okay.
also
Uh,
the homologous points may not have the same hydraulic property ratio. So how these are also incorporated in prediction the results? That is
yeah,
velocity
yes.
ratio may vary from discharge ratio. That hydraulic property may also vary for homologous points. So how these are all incorporated?
Basically the discharge ratio will be. Let me go through this.
Homologous point. If we say homologous point may have different discharge ratio or different velocity ratio, there is also possibility of this distortion.
We have not really gone that much deep while doing
Yes, sir.
these studies.
Yes,
Okay,
sir. Not a
so
study.
let
Yes,
me.
sir. Okay, okay,
Yeah,
sir. Okay.
it is
Uh,
not that. Uh, Tell
yes, sir.
me.
Yes, sir. Okay, thank you, sir. Thank you. So one more question is there, sir.
Uh,
Is there any change in the regime of river due to construction of bridge when it basically when we compare with the change in the regime due to construction of weir, etc.?
okay. No, actually, because of the construction of this thing, there will be an increase. There will be an afflux of around some 3 to 4 centimeters. Okay, upstream of the bridge. Okay. So that will be felt maybe around 1 to 1.5 kilometers. Afterwards, this regime is